Well, first of all, who is Henry Poincare? Born April 29, 1854, and died on July 17, 1912. He was a French mathematician, theoretical physicist, engineer, and a philosopher of science. He was responsible for formulating the point. He is often described as a polymath and in mathematics as the last universalist by Eric Temple. Since in his research on the three-body problem, Poincare became the first person to discover a chaotic deterministic system which laid the foundation of modern chaos theory. He is also considered to be one of the founders of the field of topology. The Poincare conjecture states that every simply connected closed three-manifold is homomorphic to the three-sphere S cubed, where a three-sphere is simply a relation of the usual sphere to one dimension higher. In other words, the conjecture says that the three-sphere is the only type of bound three-dimensional space possible that contains no holes. This is a statement about topological space. Let's define each of the terms in the conjecture. Simply connect space. This means the space has no holes. A football is simply connected, but a donut is not. Technically, we can say that pi sub 1 of x is 0, but I'll explain this notation further on. Closed space. The space is finite and has no boundaries. A sphere is closed, but the plane is not, because it is infinite. A disk is also not, because even though it is finite, it has a boundary. Manifold at every small neighborhood on the space, it approximates Euclidean space. A standard sphere is called a two-sphere because it is actually a two-manifold. Its surface resembles the 2D plane if you zoom into it so that the curvature approaches zero. Continuing this logic, the one sphere is a circle. A third sphere is very difficult to visualize because it has a 3D surface and existing in 4D space. Homeomorphic is one space is homomorphic to another. It means you can continuously deform the one space into the other. The two sphere and a football are homomorphic. The two sphere and a donut are not. No matter how much you deform a sphere, you can get that basket hole in the donut and vice versa.
Now I will explain how do you show that two spaces are homomorphic to each other. One way is to show that the space share the same fundamental group. A group have a little more further explanation, but basically it's a collection of elements which include an identity element and a product. Also, each element has an inverse. The fundamental groups basically describe how many ways can draw a path in a space. It is organized as follows, where each element is a path which starts and ends at the same point. The identity fundamental groups is the trivial path of length 0. For example, a single point, the product in the fundamental groups is just combined from two paths end to end, since all paths start and end at the same point. You can always take their product and get a new element in the group. The fundamental group of the NFR is equivalent to the group with identity element, because any path can always be shortened out into a single path due to the fact the NFR have no hole. The fundamental group of the NFR is equivalent to the group with identity element, because any path can be always shortened down into a single point due to the fact the NFR have no hole, such I can receive in the image. If a space fundamental group is trivial, then that means it is simple connect have described above. To say the fundamental group for any NFR is trivial, you use the following notation, where P means this group contains elements of one-dimensional closed path. A little bit off topic, but even more fascinating is that you can also determine a higher dimension path, and there is no fundamental groups develop an interesting and complex structure. The Poincaré conjecture says that if we for any 3 manifold m to the power 3, it's P1 in m to the power 3 equal to 0, then m to the power 3 can be continually be forming into s to the power 3. Perelman finally solved this for 3 manifolds by using Ricci flows technique to show that their manifolds are homeomorphic.